Hello, GCC Chem 107 students. This is the PowerPoint and lecture for Chapter 10. This is my favorite chapter. It's over nuclear weapons, power, and medicine. So I hope you enjoy it as much as I do. So people are often scared of the word nuclear. They think it means bombs and explosions and radiation, and all the negative things tend to come to mind first. However, 20% of our U.S. power comes from nuclear power plants, and in the United States, we've never really had an accident. Also, every day, nuclear medicine saves people's lives. It is used to treat cancer, and it's also used in a lot of testing and diagnostic testing that finds problems that can then be solved. So it is a really important part of our medical makeup these days. And then nuclear power plants also don't emit greenhouse gases. So that's great because our coal power plants are polluting this world and emitting greenhouse gases, which is causing climate change, which is going to destroy the planet if we don't do something. And nuclear power plants don't emit any greenhouse gases at all. Also, they can operate 24/7. So that's better than solar and wind, which don't operate all the time. So there's some really good things about nuclear power plants. So there's some good things about the word nuclear. It's not all just scary bad stuff. So the first thing we're going to learn about is fission. Fission has an I in it, and it means splitting, which has an I in it. So fission is when a large atom splits into smaller atoms, and it releases a lot of energy. So it was some Germans that discovered the fission process when they were bombarding uranium atoms with neutrons back in 1938. So that's a long time ago. And they discovered that the uranium atom would split. So fission can happen naturally, and in fact it does. There are naturally occurring atoms that undergo fission, or we can induce it. That means we make it happen. It's man-made. So like the Germans did, you can bombard some atoms with neutrons and they will undergo fission because you made them. So inducement. A couple of atoms that undergo fission you may have heard of. Uranium and its dash 235. Remember, that's the atomic mass, and that's the number of protons plus neutrons, 235. And then also plutonium. You may have heard of plutonium. Plutonium 239 can undergo fission. Again, that's the number of protons plus neutrons, the 239. And so uranium and plutonium has a couple of isotopes that can undergo fission. So remember what fission is. That's important. So here's a reaction showing fission. Now you don't need to be able to memorize this, but what you can see happening in this reaction up here is we start out with a 235 uranium. Now the 92 is from the periodic table where uranium is. Uranium's down here on the bottom. And 92 is just the proton, so remember that. So 235 is the mass. It's the protons plus neutrons. 92 is the protons only by themselves. Protons only. And so the top number is mass, the bottom number is the protons for uranium. But if we hit it hard enough with a neutron, it'll split. And it'll make a couple of other atoms, Kr, krypton, and Ba, barium, and also 3 neutrons result. Well, those 3 neutrons can go and hit more uranium atoms. So they can go hit 3 more uranium atoms, which will then fission and will produce 9 neutrons. And those 9 neutrons can go and hit 9 uranium atoms, which will then produce krypton, barium, and 27 neutrons, and so forth. So this is a self-propagating reaction, meaning once it gets started, it'll continue on its own. And we call that a chain reaction. So fission is a chain reaction. And you can see in the little picture, all we need is one little neutron to go and hit that nucleus of uranium. And boom, we get our krypton, our barium atoms, and then 3 new neutrons. Those 3 new neutrons can go and do fission again. So it's a chain reaction that escalates, right? It builds up times 3 every time. So the chain reaction will continue and build up more and more energy until we have a nuclear explosion if, and only if, we have critical mass. So if we run out of uranium before the explosion, then we can't have one. So we have to have enough uranium, it's called critical mass, in order to actually have a nuclear explosion. So critical mass is defined as the minimum amount of fissionable material, uranium, needed to cause a nuclear explosion. The critical mass of uranium-235 is 52 kilograms, or about 115 pounds. 115 pounds. That's kind of a lot. Okay, so you have to have kind of a lot of uranium to actually have a nuclear bomb. So remember that. We have to have critical mass in order to have a nuclear explosion. Now, the critical mass of plutonium-239 is much smaller. It's just 22 pounds. But again, we have to have at least that much in order for it to explode like a bomb. So let's look at uranium and fill in these blanks using our periodic table. Uranium has blank protons and blank electrons. So all you have to do is look in the periodic table and find U for uranium, and the whole number is 92. That means we have 92 protons and 92 electrons. So uranium comes in two isotopes. That means it's still uranium, but it has different masses. So uranium-238 is the most abundant. That's the one we have the most of. Uranium-235 is the least abundant, so there's less of it. How many neutrons are in these? Well, remember the 238 and the 235 are protons plus neutrons. So we need a calculator to answer this. So how many neutrons there are? Do you remember how to find neutrons? You take your mass, 238, and subtract your protons. So minus 92. So uranium-238 has 146 neutrons. Now let's try uranium-235. 235 is the protons and neutrons minus the 92 protons equals 143 neutrons. So again, mass minus protons equals neutrons. So this is fair game for a quiz or the final now, because we've talked about protons, neutrons, and mass again. Okay, what about electrons? Electrons and protons are the same. So there's 92 electrons in a uranium atom. Remember, electrons and protons are the same. Atomic notation. That's just where we put the top number as the mass, the bottom number is the protons, and then the symbol. So 238 on top, 92 on the bottom. Uranium is one isotope, and 235 on top, 92 on the bottom. Uranium is the other isotope. Now, it's hard for me to type the numbers right under each other, but they should be. Okay, it's just hard for me to type that, so they're a little off to the side. But the 238 should be right above the 92 if you were writing this down. It's hard to type that. All right, so again, protons, neutrons, and electrons, atomic mass are all fair game for the final and your Chapter 10 quiz. What can we do with fission? Now that we know big atoms can split and release enormous amounts of energy, what can we do with it? So fission creates large amounts of energy, and if we have the critical mass, it can cause a nuclear explosion, which is different from like a dynamite explosion. A nuclear explosion is much, much bigger with a lot more energy, much more dangerous, will kill a lot more people. So what do humans do with this knowledge? Well, they make bombs, right? They make bombs out of it. So we can produce bombs by having 115 pounds of uranium, so that we purposely have critical mass, so we will have an explosion. So that's a nuclear bomb. Now, the uranium-235 needs to be concentrated to 85%. That's called weapons grade uranium. We need to get rid of the 238. The 238 uranium won't explode. So we have to concentrate that uranium-235 in order to get it at least 85% pure to make a bomb. It doesn't come this way, so you can't just go dig up uranium and make a bomb. If you dig up uranium, most of it is 238, not 235. Only 235 explodes like a bomb. So you have to have special machinery to concentrate it called a centrifuge. And there are treaties about which countries are allowed to have centrifuges and which are not. It's very big, complex, expensive machinery. So again, you can't just go dig up uranium and make a bomb out of it. So what else can we do with fission? Well, we can produce electricity with it by not having critical mass. Let me say that again. In a nuclear power plant, we do not have critical mass, meaning the nuclear power plant cannot explode like a bomb. And that's a big misconception people have. Most people are scared of nuclear power plants because they think they can explode just like a nuclear bomb. False, wrong. They cannot. They do not have critical mass. Why would we have critical mass at a power plant? That's stupid. It's risky, so we don't. So we have less than critical mass at a power plant, and we just take all that energy and turn it into electricity in a power plant. In a power plant, you only need 3% uranium-235. Is that bomb quality? No. Bomb quality uranium is 85% uranium-235. You only need 3% uranium-235 in a power plant. So it's not even the right concentration of uranium to make a bomb. So we don't have critical mass, we don't have the right percentage, so we can't explode like a nuclear bomb in a power plant. By the way, when you dig uranium from the ground, it's only 0.72% uranium-235 to begin with. Okay, so naturally uranium is only 0.72% uranium-235, which is the kind we need in a power plant or a bomb. So we have to concentrate it to 3% for a power plant, but you have to concentrate it all the way to 85% to make a bomb out of it. So very different concentrations or percentages of uranium. To create a fission bomb, first of all, you have to have critical mass. Now, uranium-235, we just said, is naturally mined at 0.72% from the ground. But you have to concentrate the uranium-235 isotope to 85% pure to make a weapons-grade uranium to make a bomb. Uranium-238 is the major component of uranium ore that we get from the ground, but it's not fissionable. So the uranium-238 and the 235 must be separated from each other. And as I mentioned, it's a very complex, big machine called a gas centrifuge. The gas centrifuge uses a large number of rotating cylinders in series and parallel formations. Each cylinder's rotation creates a strong centripetal force so that the heavier gas molecules containing 238 move towards the outside of the cylinder, and the lighter gas molecules rich in 235 uranium collect closer to the center, so eventually we can separate the 238 from the 235. So that's how the centrifuge works. Now, one of these bombs is equivalent to about 20,000 tons of TNT, which is dynamite. So like I said, a typical construction bomb is not the same as a nuclear bomb. We've only used nuclear bombs in wartime twice. It was in World War II. It was the United States of America, and we dropped 2 bombs on Japan. On August 6, 1945, a bomb named Little Boy was dropped in Hiroshima. It was a uranium bomb. And then on August 9th, 3 days later, 1945, a bomb named Fat Man was dropped on Nagasaki. That was a plutonium bomb. Those are the only 2 bombs we've ever dropped on people. Now we've had over 2,000 test detonations. Those are done in remote parts of the world or in the ocean. Countries that are allowed to have nuclear bombs are the United States, United Kingdom, Russia, North Korea, China, India, France, Pakistan, and Israel is suspected to have them, but they won't admit it. So those are the countries that have the bombs, whether we like it or not. So by the way, a fission bomb is also known as an atomic bomb. So these fission bombs made out of uranium and plutonium are often called atomic bombs. Here is the mushroom cloud from the Nagasaki bomb, the Fat Man bomb. This is 11 miles up in the air. Here's a picture of the Fat Man bomb. It weighed 11,000 pounds. And if you had a person there, it's a little taller than a person, just to put it to scale. Here's the little boy explosion. Again, this is way up high in the atmosphere. And here's a picture of the little boy bomb. It is 9,700 pounds, and to put it to scale, it's about 10 feet long. So how the fission bombs work. Now, you don't keep the uranium or plutonium together in a critical mass unit. That would be stupid because it might accidentally go off. So you keep the uranium or plutonium fuel in subcritical masses that are kept separate until we arm the bomb and it's ready to explode. The neutrons come from a generator and they don't start until the fission reaction is ready. We separate them from the uranium fuel by foil and remove the foil when we set the bomb to explode. The energy created is about 10 kilotons of dynamite, TNT. So there's two types of fission bombs. The top one is the gun type assembly method. You have two big pieces of uranium-235 in blue separated by the white area, and they're not touching, so it's not critical mass. It can't explode until they're squeezed together. What we do at the other end is we arm the bomb with a little explosion that pushes the piece of uranium closer to the other piece of uranium so we have critical mass. So again, the bomb is not armed until we do this. So to arm the bomb, we basically have a squeeze play. We have an explosion and we squish the uranium together until it comes together, and then we have critical mass. We can pull the foil, let the neutrons hit, and get that chain reaction going. Now, my favorite one is the implosion assembly method. It's like a piece of pie that's been separated from each other. So if you look at the circle right here, it's like we had pieces of pie and we pulled each piece back. And now what we do is we have little explosions around the circle that push the pieces of pie back together in the middle. Once they're back together, we have critical mass, so we're allowed to have the explosion. So again, here's another picture of the gun barrel assembly method. We have our uranium bullet that goes into the other end, and together it makes critical mass. And here's my favorite one, the pie one, the spherical one, where we push all the pieces of pie back together in order to have the critical mass. There was a test bomb in 1957 near Las Vegas that had 2 times the energy of Little Boy. Look at that mushroom cloud. Whew! And I'll tell you what the brown color is in a little bit. All right, so we're going to stop there for our first video for Chapter 10. I hope you found nuclear bombs exciting. We're going to talk more about bombs and about power plants in our next slide. So goodbye.